Howdy, I'm Hasib Bajwa. This presentation is my final project titled Drop Test Comparison of Shock Mitigation Designs. In this study, I compared three structural configurations, which are rigid, spring-based, and twisted tower, to evaluate how effectively they reduce transmitted vibration during vertical drop impacts. For this study, I conducted a total of 37 vertical drop tests using different structural configurations. As mentioned before, the rigid setup had no damping. Each drop test was performed under controlled conditions and acceleration data was recording using IMU. Here in this video, you can see that the minute it hits the ground, the IMU records 1 second of data, and that data is used to compute the RMS value for all the 37 runs. The objective of this project is to determine whether structural design affects impact response. The independent variables or inputs are the design type, which are rigid, spring, and twisted tower, and the drop height, which is 0.25 meters and 0.5 meters. The dependent variable or output is the 1 second RMS acceleration, which where lower RMS values indicate better shock mitigation. The null hypothesis is that the mean RMS acceleration is equal across all three designs, while the alternative hypothesis states that at least one design has a different mean RMS acceleration. The methodology consisted of controlled vertical drop tests conducted at two drop heights, with multiple repeated trials for each design to capture variability. For each test, the 1 second RMS acceleration was calculated using the post-impact acceleration signal, as I mentioned before. To statistically evaluate different designs, one-way ANOVA was performed separately at each drop height. In addition, box plots were used to visually examine the distribution, variability, and consistency of RMS acceleration across the designs. The ANOVA results show different behavior at two drop heights. At 0.25, the p-value is 0.081, which is greater than the 0.05, so the result is not statistically significant, and we fail to reject the null hypothesis. This indicates that at a lower impact energy, the designs do not differ significantly in mean RMS acceleration terms. At 0.5 meters, the p-value is very small. It is less than 0.05, which is much smaller, which is highly significant, and we reject the null hypothesis. This shows that the structural design has strong and statistically significant effect on RMS acceleration at higher impact energy. Starting with the 0.25 meter box plots, the distribution for the rigid, spring, and twisted tower overlap significantly. This overlap indicates that the designs behave similarly at low drop height, which supports our ANOVA result that the p-value was greater than 0.05. Looking at the 0.5 meter box plots on the right, the differences become much more pronounced. The rigid design shows highest RMS acceleration values and a wider spread, indicating higher transmitted vibration and greater variability, while the spring design shows the lowest RMS values and tightest spread, demonstrating effective and consistent shock mitigation. The twisted tower design lies between the two, reducing acceleration compared to the rigid configuration, but not as much as the spring system. So in conclusion, At 0.25 meters, we fail to reject the null hypothesis because the differences among designs are not statistically significant at low impact energy, which is 0.25 meters. At 0.5 meters, we reject the null hypothesis, confirming that the structural design has a statistically significant effect on RMS acceleration under high impact energy. Overall, the spring-based design performs best, then the twisted tower design provides intermediate improvement, and the rigid design performs the worst. These results show that design choice becomes increasingly important as the impact energy increases. Thank you.